What specific problem does log linear attention aim to solve, and how does it improve upon the limitations of existing linear attention mechanisms?
Log linear attention addresses the limitations of existing linear attention mechanisms, particularly their fixed-sized hidden states, which hinder capabilities like associative recall over longer contexts. By maintaining a growing set of hidden states that scales logarithmically with sequence length, log linear attention allows for more effective context utilization, especially in longer sequences where traditional linear attention tends to degrade in performance. This mechanism employs a hierarchical matrix structure, specifically through Fenwick tree partitioning, which enables subquadratic training complexity and logarithmic memory cost. Consequently, log linear attention not only enhances the model's ability to capture multi-scale temporal structures, but also improves computational efficiency, making it more suitable for practical applications involving long sequences. Overall, it provides a more expressive and efficient alternative to linear attention, particularly in scenarios requiring robust long-context understanding.
How does the proposed log linear attention method work? Illustrate the step-by-step process of its computation and how it leverages the Fenwick tree structure for hierarchical segmentation.
The proposed log linear attention method operates by modifying the masking matrix to enable efficient computation while maintaining the ability to capture long-range dependencies. The process begins with the input sequence being partitioned into segments based on a Fenwick tree structure, which allows for hierarchical segmentation into power-of-2-sized buckets. Each bucket summarizes a range of tokens, enabling the model to attend to a logarithmic number of hidden states that represent past context at multiple temporal scales. During computation, the model calculates the recurrent memory separately for each bucket and weights the output using data-dependent scalars, which are parameterized as functions of the input. This structured approach not only enhances the model's ability to utilize recent tokens with higher resolution, but also ensures that the overall time complexity remains log linear, while the memory cost is logarithmic, facilitating efficient training and inference.
Can you provide a detailed example that demonstrates how log linear attention processes a sequence, including how it manages the hidden states and weights contributions from different temporal scales?
Log linear attention processes a sequence by employing a Fenwick tree-based partitioning scheme that divides the input into power-of-2-sized segments, allowing the model to maintain a growing set of hidden states that summarize information at multiple temporal scales. For each token in the sequence, log linear attention computes a recurrent memory separately for each bucket created by this partitioning, where each bucket captures a range of past context. The contributions from these buckets to the output are weighted by data-dependent scalars, which are parameterized as functions of the input through a linear projection. This mechanism enables the model to adaptively attend to different temporal scales, emphasizing recent tokens with finer granularity while still maintaining a logarithmic number of hidden states. Consequently, the output is generated by aggregating these weighted contributions, allowing log linear attention to effectively utilize long-range context while managing memory efficiently.
What are the theoretical or practical benefits of using log linear attention over traditional linear attention and softmax attention, particularly in terms of computational efficiency and memory usage?
Log linear attention offers significant theoretical and practical benefits over traditional linear attention and softmax attention, particularly in computational efficiency and memory usage. The compute cost of log linear attention is log linear in sequence length, while its memory cost is logarithmic, which is a substantial improvement compared to the quadratic compute and linear memory costs associated with softmax attention. Additionally, log linear attention maintains a growing set of hidden states that scales logarithmically with sequence length, allowing for more effective context utilization, especially in longer sequences. This structure enables a matmul-rich parallel training algorithm that is hardware efficient, leading to practical wall clock improvements over optimized implementations of softmax attention. Furthermore, log linear attention's hierarchical partitioning via Fenwick tree allows for adaptive attention to different temporal scales, enhancing the model's ability to capture long-range dependencies without incurring the high costs typical of traditional attention mechanisms.
How was log linear attention validated in the experiments? Describe the datasets used, performance metrics, and how the results were compared to baseline models.
Log linear attention was validated through a series of experiments on various datasets, including multi-query associative recall, MQAR, academic scale language modeling using the long data collections dataset, and several standard benchmarks like Wikitext perplexity and zero-shot common sense reasoning tasks. The performance metrics included accuracy on the MQAR benchmark, perplexity for language modeling, and task-specific metrics for common sense reasoning and in-context retrieval tasks. Results were compared against baseline models such as DeltaNet, Mamba2, and parameter-matched transformers, with log linear variants showing improved performance in long context tasks, particularly in maintaining accuracy as sequence lengths increased. For instance, log linear DeltaNet consistently outperformed its linear counterpart, especially in long context scenarios, while log linear Mamba2 demonstrated significant gains across multiple metrics in the needle in a haystack benchmark. Overall, the experiments highlighted log linear attention's effectiveness in enhancing long-range context utilization compared to traditional linear attention models.
What limitations or challenges were identified with log linear attention? Discuss any specific tasks where it did not outperform linear attention or where engineering complexities were a concern.
Log linear attention, while improving upon linear attention in many scenarios, still faces limitations, particularly in tasks where it did not outperform linear attention baselines. For instance, the paper notes that there are several tasks where log linear attention did not show improvements over linear attention, although specific tasks are not detailed. Additionally, the engineering complexity of log linear attention is higher. Inter-chunk computations resemble multiple applications of linear attention primitives, while intra-chunk operations require bespoke implementations, complicating the backward pass due to the need to compute gradients for both standard attention components and the additional terms. Furthermore, the use of Fenwick tree partitioning introduces an inductive bias that allocates more fine-grained memory to recent tokens while compressing distant tokens, which may not be optimal for all applications. These challenges highlight the need for further exploration of parametrizations and flexible structures to enhance performance across various tasks.